Okay, so for our mechanics question today, we are going to handle some static rigid bodies. So static rigid bodies, static meaning that they're not moving. So we're going to see the word equilibrium pop up. Rigid, so this is about things like beams, rods, ladders. This is things that don't bend. But for you, what this really means is it means that there are going to be moments involved. Okay. And bodies just means the objects themselves. So here we go. We've got a diagram where we've got the typical situation, which is sort of a ladder, and it seems to be connecting, so touching the ground and a wall. So here we go. A uniform rod. So uniform means that the weight acts in the middle. So if it has mass M and it's 8 meters, what that means is it means sort of halfway up. So I'm going to write 4 meters here. It's got a force of mg acting downwards. Okay. Also, the inclusion of the word rod here meant that I have a question that is about static rigid bodies. Okay. So a uniform rod, it rests in equilibrium. So how will equilibrium come up? So equilibrium will give us sort of a situation where we'll be considering up equals down, left equals right. In other words, the resultant moment vertically and horizontally is 0. But it will also give us this one, which is that the clockwise and anti-clockwise moments are equal. These are the 3 fundamental conditions for any sort of ladder problem. Okay, so it rests in equilibrium with end A on rough. Rough is a key word. It means that there will be friction. So on rough horizontal ground. Okay, so what we're drawing here is we're drawing all of the forces acting on this ladder. Okay, so what the ground will do is the ground will push the ladder up. So I'm going to call that R. And because it said rough, it means that there's friction. So I'm going to draw it like this. The reason why is if you kind of picture this ladder against a wall, the ladder sort of wants to slide down. Okay, so the friction is going to be sort of pointing towards the right. It's resisting the direction that it wants to go. Okay, you could write friction here as well, but I tend to just sort of write mu r on these ones. There's a smooth vertical wall. Okay, so the wall is the other part of this. So the wall is a bit like a surface, right? Surfaces give off a normal reaction. So R comes from the ground. Well, from the wall, you'll get a different one. So I'm going to give it a different letter. I'm going to call it S. Okay, so a different reaction. It makes a 30-degree angle. Okay, so in these kind of questions, it's often good to just write out your values because you're going to be using these. So that's a half, and that's a √3 over 2. Okay, I think that's it with all the information at the start. So this is the kind of basic diagram. You may wish to sort of draw another 4 on there. This is our basic sort of diagram that I would normally draw. And now we're going to need to move on to our conditions. So up equals down, left equals right, clockwise equals anti-clockwise. For the first one, it says, show that the normal reaction at the wall, that's S, is this figure here. So we could just think about which of these might be the best one to start with. So moments are interesting in that where you take moments, and you will almost always take moments from the ground, where you take moments, you essentially ignore the forces there, which would be those ones. And the reason for this is when you calculate moments, the calculation has distance, and these have a distance of 0. So you can effectively kind of just ignore these ones, which leaves you a question that would have just those 2 forces there. So because I can see mg, and S is the thing in question, I think I'm going to start with moments. I think that makes the most sense. So what we're going to do here, so I'm going to do moments at A, and I'm going to do all of the clockwise equaling all of the anti-clockwise. So if you imagine that you're here, what are the forces? Well, you're going to ignore these, as we said. The first force that you come up against is this mg force here. Now, there's a bit of a problem. The problem is that the distance is like this and the force is like this. So this angle is not a right angle. And when you do moments, the calculation for a moment is moments are the perpendicular, and this can be perpendicular distance or perpendicular force. I'm going to do perpendicular force times distance. So because I currently don't have that, that requires a little bit more work from me. So what I'm going to do here is I'm going to resolve this force mg. So that's how I could actually resolve it to give me a right angle. That would be theta. And this one here is the adjacent side. So this is the cos side. So this is mg cos theta. Now, unlike inclined plane questions, I probably don't actually need that one there. Okay, so now I've resolved it. I'm just going to cross that one out. So, no, actually, I'll leave that there. I'm going to just have it in purple instead, so I can sort of see that I've got my forces ready now. So let's do the moment. The moment is the distance, don't forget the distance, very easy to do that, times the force. So that is mg cos theta, and I'm going to put times 4. Okay, what's that going to be equal to? Well, the next force is actually this one up here. And there's a similar problem again, that the angle's not working. So what I'm going to do is I'm going to resolve this one. And I'm going to resolve it like this. Notice that the arrow that I resolve adds up to be overall the same as this one here. This is theta. So this is the opposite part. So this part here then will be s sine theta. Okay. So when I have s sine theta, it is now sort of perpendicular. And it's ready for me to use. So that is what kind of moment? That wants the ladder, well, this wants the ladder to go this way. That wants the ladder to go that way. That's an anti-clockwise moment. So let's write that down. That's S sine theta. And how far away is it? It's 8 away. So now let's clean this up a little bit. I'm going to put root 3 over 2, or should we even put 4 root 3 over 2 mg equals over here an 8, and a sine theta is a half, so I'm going to write 4s. And finally, those 4's cancel, and you can see that that leaves me with root 3 over 2 mg, which is what s is. Okay, so that was using this condition here. And what will probably happen now is in the rest of the question, I use the other parts, and this sort of line here will be useful. That tends to be how the questions go. So find the coefficient of friction. Well, that's mu is what they're asking for here. So it seems to be about horizontal forces. So now we're going to do our second condition, this one over here, okay, which is all of the left forces equal all of the right forces. So let's write down left equals right. So all of the forces left is S. So I'm not using the resolved version. I'm using the original version now because it's horizontal. So S. And then that's actually it, isn't it? It's just equals mu R. Okay. S, I actually know what S is, but R, I don't know what R is. So what we're going to do finally is we're going to do up equals down, and we're going to find that that helps us out. So up equals down. All of the up forces would just be R. And the down force would be mg. So now we have this one as well. So we're going to substitute in our results in those blue boxes there. So that's going to give me what? That's going to give me root 3 over 2 mg equals mu mg. And the mg's actually cancel, don't they? Fully. So the value for mu is root 3 over 2 or I think it ends up being something like, what does it end up being? Ends up being 0.866 or 0.87. Okay. So this is the first sort of basic situation of a ladder. Yeah. So one of the most common ones that you could have. We could have more people sitting on the ladder. If we had more people sitting on the ladder, it would just sort of add a few more forces. But you're going to find that largely you do these sort of 3 steps. So I'm going to give you a moment now just to have a go at a similar question for yourself, which is as follows. And let's have a look at the working out after we do a quick force diagram. So your force diagram for this is largely going to look quite similar. So the basic is, if you have a ladder on the ground, you have something like this. The mass is 25. It is uniform. So you would have 25 G. Okay. You would do the same for the resolving here. So this would be 25G cos theta. And on this one, instead, you also have a painter standing on the ladder at C. So what would that do? Well, if I just tidy this up a little bit, just to show you. So this will still be 25G cos theta. But if you have other people standing on the ladder, you'll just have other down arrows like this, which you will also, for your moments, you'll need to resolve. So the painter is 70G. Well, you know, how about this? Can we just jump straight to that result there? So you would get, for example, 70G cos theta. And that should kind of give you what you need to start setting up the question. Anything else you need to do on here? Well, it's got one of these, hasn't it? So a nice way to resolve one of these tan theta ones is you draw a triangle. Opposite over adjacent is 5 over 12, so that's a 13. Okay, and now you write your values that you're going to inevitably use later on, which would be opposite over hypotenuse. That's the 5 over 13, and this must be the 12 over 13. Anyway, so now we've got the idea. Let's sort of have a look at the neat version of the working out that you should hopefully be able to do from that force diagram and the same steps. Okay, so they've kind of called these the forces. So I would normally use mu r there, n or s. Okay, these are equivalents. And what have we got here? So we've got a few things going on. Let's do the resolving forces first. So vertically, we're going to say that we've got the weight of both people, which should end up being 931. And that's going to be equal to the floor. So that's the first one that you could do. You could instead write this as well as 90, I believe this was 95G. Okay, horizontally, you've got the friction, which you might also call mu r equal to s. So you're going to end up with that equation there. And the part that really breaks the question forward is taking about the moments. Okay, so we've got our clockwise and our anti-clockwise moments. So you should end up with this number here for at the wall. Okay, and is this one at the wall? Yes. And this should be your moments for the other part. Okay. So I hope you found that you were now able to kind of start working them through. The basic situation is as you can see here on the screen. So get your forces, work through your 3 conditions, and that's how you can handle one of the first key situations for static rigid bodies.